The Sun, like the stars, draws its energy from the fusion of hydrogen atoms. This nuclear reaction is 1 million times more energetic than the strongest of all chemical reactions. Since the early 1950s, scientists have been drawn to this powerful energy source and have sought to recreate it on Earth. The stakes are enormous. Fusion could provide a source of large-scale energy, one that is safe, available anywhere on Earth, in unlimited quantity, and with no negative impact on the environment. The fusion adventure began in the 1950s with a young Russian soldier called Oleg Lavrentiev, who first proposed the idea of a fusion machine based on the thermal insulation of high-temperature plasma using a high-voltage electric field. In the following years, many fusion machines were built and tested in the Soviet Union, the United States, Europe and Japan. These initiatives were triggered by the first major oil crisis. The hunt for a new energy source had begun, both in the public and the private sectors. Despite the progress, it soon became clear that when it comes to fusion, size matters. A bigger machine was needed. Through the ITER project, 6 nations, China, India, Korea, Japan, Russia, the United States of America and the European Union have agreed to pool their financial and scientific resources to prove the viability of fusion as an energy source. ITER is the Latin word for the way. Its goal is to pave the way to fusion power. From 50 megawatts of input heating power, ITER will produce 500 megawatts of thermal power for at least 300 seconds, the first fusion machine to produce net energy. The chosen site was in southern France. And so, here we are today, building the largest fusion machine ever. ITER is based on the tokamak concept of magnetic confinement. First, the fusion fuel, puffs of deuterium and tritium, is injected into a vacuum vessel. Then a powerful magnet, centered in the core of the machine, is turned on, inducing a current across the gaseous mixture. The voltage rips electrons from the atoms, forming a particle soup called plasma. Now the superconducting poloidal and toroidal coils are ramped up, locking the plasma inside the vacuum vessel. Squeezed together, it quickly heats up to 10 million degrees centigrade, but that is not good enough yet. To make the particles fuse, the temperature needs to be increased further. Radio and microwaves are fired into the plasma together with high-energy beams of deuterium atoms, until the plasma reaches 150 million degrees. Hot enough. The products from this reaction are helium and highly energetic neutrons. While the helium particle remains in the plasma, helping to keep it hot, the neutrons escape the magnetic confinement and hit the surrounding metal wall. Once they have slowed down, the neutrons release their energy by emitting heat, which is finally turned into electricity. While work progresses in southern France, manufacturing begins in ITER member factories all over the world. Instead of providing the monetary value of each system or component of the ITER machine, the member states will deliver the completed components to the ITER site, where they will be assembled in what is certainly one of the most complex jigsaw puzzles ever conceived. The largest components will arrive by sea and be unloaded near Marseille. From there they will travel to ITER along the 100-kilometre ITER itinerary, which has been especially adapted by France to receive the exceptional size and weight of the loads. The delivery of the first completed components is scheduled for 2014. From that moment on, approximately 6 years will be necessary to complete the assembly, testing and commissioning of the machine. Back at the construction site, mighty bulldozers and towering cranes dominate the scene. Just a few years from now, ITER will tell us if the dream of a limitless energy source can finally become reality. The 35 nations united under the ITER flag believe that fusion is the future. And so do we.